So in the last lecture, we talked about the work done by the variable force, right? So in the variable force, we saw the work done by various forces like tangential force, force like yeah, I mean force which changes the magnitude, force which can also change the direction. So all comes into the category of variable force. And the rule is whenever we need to calculate the variable force, I mean work done by variable force, we need to do this in elementary step, which means if you know the force is changing either direction or changing either magnitude, so whether you are changing the direction or magnitude, you need to only write dw instead of w. Okay, so you're not supposed to write w at once. You cannot write f dot delta. Okay, you can only write f dot dr. So today we are going to talk about some other variable force. It could be variable gravity, it could be variable friction as well. So how we do it? Okay, so I would like to solve particularly something called the chain problems. Okay. So imagine you have a chain given to you and chain is completely on the table. So the mass of the chain is m and the length is a. Okay. Now after some time, in a subsequent motion, what you see is that a part of the chain is hanging, and the hanging part let's call X, and the remaining part is L1/6. Now there is a question. So we can also choose X as the upper part and L-X as the lower part, right? So how to choose the variable correctly? The answer is always choose something which is increasing in nature. So you can see as time will progress, the hanging part will grow, whereas the part on the table will shrink. So variable should be given name to the part which is growing in value with time. So it's like a not necessary, but this is most convenient way of assumption. So you should know that how to assume things. Now, in case of when we don't have a point mass, we have something called distributed mass because the mass is spread over the length of the chain. We define something called linear mass density by a symbol lambda, and lambda we write as L by M by L, mass per unit length. So if mass is uniform, we write M by L as lambda. In general, for uniform mass distribution, but in general we write as dm by dl. So the mass of the elementary length dl, if dm is the mass, so lambda of that elementary location is dm by dl. So generally it is given sometime as a variable. Let's say the give you lambda is lambda not x, which means as x will increase, x not this x, I mean it could be some other symbol. So let's say if I have a chain or maybe something else, and if I call this as x-axis, and if I say lambda equals to lambda not x, which means if you move x distance away and if you cut a dx length, the mass of this elementary rod will be dm, and lambda of that location, lambda of mass at x location, which is actually dx. So we call lambda x, lambda of x. Like so you say f of x. So lambda of x is dm by dx. So in such case, you need to write dm equals to so this kind of calculation you also need to know. And now what you can do is, now you can see the what is the hanging part. So gravity, okay, right now x length is hanging, and what we need to do is imagine subsequently it goes down by dx. So if something goes down by dx, what is the work done by gravity? Elementary work done by gravity. So the gravity force acting on this is only mg, and the hanging part is only the weight providing to the gravity, right? Because the part on the table is at rest in the vertical direction. So normal will balance the mg, right? So what is this mass? The mass on the table? Lambda into L minus x, which is the mass per unit length into g. This is normal. And this hanging part will have its own mass. How much? This mass is how much? Can you guess? How much should be this mass? Tell me.
Lambda x. Lambda x.
Lambda x. Very good. Just lambda x. Lambda is the mass per unit length into x, or you can
Yes.
say m by L into x. So the gravity force acting here is how much? M dash g, which is lambda x into g. So the work done we can attach, because force is acting downwards, so work we can attach lambda x into g into dx. So this is how you write the elementary work by the gravity. And then the next step is you have to integrate. So lambda g we can take common, we have left with x dx. And x will go from, you can go from 0 to x or 0 to L, whatever, up to whatever length you want to hang. So you can find the work done, and you can see that the answer is something very interesting. It is x square by 2. So it is mg x square by 2L. Now, if the entire length of chain will kind of hang, till that time, what is the work done by gravity? Like how much gravity will do the work till the chain leaves the table? So this is a very common question. Work done by gravity till it leaves on chain, till it leaves the table. So in such scenario, the x will be equal to how much? L, correct? So you can put x equals to L. What will you see? mgl by 2. And later on, you can also remember that this is nothing but the how much center mass of chain has gone down. So when the entire chain is like hanging from the table, you can see this. You can clearly see where is the center of mass of the chain. It is here. And if the entire length is L, what is the depth of this center mass? L by 2. So in future, the same thing we do it by center mass concept. We simply say that it is the location of center mass mg into location of center mass. So if it is going down, if the center mass is going down, we say work is positive, and if it is going up, we say work is negative. Is this clear?
Yes, sir.
So this is your old school formula which you studied, mgh. But here h is replaced by yc. So whatever center mass will ascend or descend will decide the potential, will decide the work done by gravity. It is not the length of object, only center mass ascent or descent. So because this chapter is mostly particle dynamics, but you will come across the chain problem, and in that case we don't solve like this. We don't integrate because that is not required. We simply locate the center mass and we write m g h. How to write without integration? So without integration, how to write? It's very simple. What is the hanging mass? M g. And what is the depth of the center mass of hanging mass?
L by 2.
X by 2 in general.
Yes, sir. X by 2.
mgh. mgh is x by 2. The center mass of the hanging part is always at the midpoint of the length if it is uniform. And therefore, you can see the answer becomes lambda g x square by 2, which is nothing but mg x square by 2. So any such question can be solved in a, you can now do it in a reverse order. No need to integrate. You simply write mgh mentally, but h should be replaced by center of mass location. Okay. So we say that the H is called the vertical displacement of center mass. Okay. So if you go up, then we see the vertical displacement of center mass. So you can as put a note that work done by gravity only depends on vertical displacement of center of mass of object, right? And the center of mass of the object will again depend on the mass distribution, its shape, size, and other things. But for a uniform chain problem, it is always at the midpoint. I hope this is okay.
Yes, sir.
Now, in the same question, if I introduced a coefficient of friction mu, so you can clearly see as the chain will try to slip right, the friction will act in which direction, guys? So
Towards left.
it will act, first of all, it will act on the chain on the table. And because it is slipping, so it must be kinetic. Okay. So you can clearly see the force is towards left, but the displacement of the chain is towards right.
Towards right.
So when we write the work done by friction in a similar case, in the same case, in the same situation, so how to write? Find the work done by friction on chain. So the way of writing is again dW F A, and because force and displacements are exactly opposite, so we write minus Fk dx. Okay. So nothing will change, everything remains same. But the Fk we can write as mu into n, correct? If you remember. But now the tricky question is, what is n here? In general, not at one instant. Tell me. Tell me.
mg.
So which m?
So lambda into x.
Lambda into. So friction will act on the hanging part or part on the table.
Part
On
of
the
the table.
table.
So n will be balancing the weight of the chain on the table, right? So how much chain is on the table when it is descending by x? Tell me.
L minus x.
L minus x, right? It is lambda into L minus x, am I right? Into G, mg, mu mg, correct? Do you realize that the normal reaction will be the weight of the part of the chain on the table?
Yes, sir.
Yes.
And you can clearly see the normal reaction here is variable, isn't it? Sorry. Normal reaction is variable, isn't it? Hello. Into d.
Yes.
First of all, do you realize this? Yes or no? Do you realize this? N is lambda L minus X into G.
Yes, sir.
So we can also rewrite as minus mu into M by L minus X into dx, or G is G into dx. And this is the elementary work. See, first of all, you need to understand whenever we have the force variable, and the force variable can be of any type. It could be of change of magnitude, change of direction. But in this case, it is change of magnitude, not direction. Direction is constant, right? So here
Yes.
direction is constant, but magnitude is varying. So direction constant, but the modulus is variable. So you're solving a question of this nature. And so you can see that if you want to get the net work done till the chain hangs by some length x, so we need to integrate this part. I would say in general from 0 to x, they will mention that 0 to L by 2, L by 4, or the limit will be given to you. And you need to actually do that limit thing, okay? So work done with friction will be minus mu mg. And I hope you all know integration, it is Lx minus x square by 2, right? Is clear?
Yes.
Okay. So let me just figure it out that can we have any pattern here? It is L minus x by 2. It is L minus x by 2 into x. Okay. L minus x by 2. What does it mean? Total length minus the length for okay. So if I'm trying to create some other interesting fact, if it is possible. So if I plot a graph of normal reaction versus x, so just try to understand the normal reaction versus x graph. Normal is how much? M by L lambda into L minus x into G, correct? So when x is 0, the normal reaction is mg, right?
Yes.
So n will have a decreasing graph, right? And when x is L, it is completely 0. So normal will decrease linearly. Can you see that? So normal is decreasing linearly. So when it is x, how much is this value? Let's put n. And you can use the similar triangle. And this is the element, this theta contact theta. So tan theta in a small triangle is how much? Normal upon L minus x. And in a big triangle is but what I'm trying to find the answer. This is not required. Can we do something graphically which can be meaningful to us? L minus x by 2. The work. Okay. The friction force is mu into one. If I simply multiply with mu, and it is mu. Hmm. How much is this area? Tell me what is this area? You can find this area, right? So what I'm doing is I'm writing the graph of FK modulus, just magnitude wise versus X. So in the graph of friction, the only mu will multiply, right? Because we know Fk is mu into n. So if you know the graph of n, you can also know the graph of Fk. And you can find the area from here to here, up to X. So this area we can calculate, right? How? So this area is, put a minus sign and put a area. Area is how much? Half into. It is like a trapezium. And this area of trapezium, you know, sum of the parallel sides. So parallel side is mu into n, which is mu into n is n by L into L minus x into G. At x distance, that is n. We have already done this part. Sum of the parallel sides plus mg into separation. So without integration, if you want to do, you have to do in terms of area, because that is the basic meaning of area under the curve, right?
Yes, sir.
So area under the curve itself gives the work done, right? So you can see that you may take mu mg common. So what you left with is mu. I think so. Mu mg is common. So L minus x by L plus 1, right? Okay. Sorry. I think mu will come everywhere. This is also here. Actually. Okay, now we're changing to graph of FK, right? I can take a mu common, just take mu common. Or we can make it even simpler. Don't make it too much messy. Yes, simple. So you can just say if I call this friction, I mean, let's call this as NF. So now this area we know how to find. Don't say this is the volume by normal. This is to write the volume of friction, we just need to write minus mu times area under the NX graph. Because mu is common. And area is half into sum of the parallel side, which is mg. plus the n at any x value is mg, L minus x by L into x. So, and if we take mg common, what we get is 1 plus answer is simple. And oh, mg I am missing here. Mg one here. Now you can see the answer is same what we got. If you take 2 inside, it is 1 minus x by 2, right? Into x. So you can see this is the same answer. It is just like we can do things. If you don't want to do the integration, you can use the graph and find the area. So for work done by friction, if the graph is variable, you have to just find the area. In that way, it will be easy. It is clear? Hello, hello, hello. It's clear, guys?
Yes.
So the area is equivalent of integration. No need to worry. This is not something surprising. That is the basic meaning of area, right? So the integration always refers to area under the curve, if you remember. So we always study area under the curve as an integration. Today we are doing the reverse process. If you are good with the integration, do it like this. But if you want to do it in terms of graph, you should be good with the graph. You should be able to draw the graph first clearly, and then you can solve it. So choice is yours. You can always use this method. So what is the total work done by friction? I think that will be easy for you, right? So in the examination, they generally ask the total work done. If they ask intermediate, then you have to do this sort of effort. But again, if you look at the normal and x graph, so clearly this is the entire game. It goes from MD to 0, right? At L. So the total work is how much? Minus mu times total area under NX graph, right? So that will reduce the effort. For total work, it is easy, right? Because beyond that, x cannot be negative, so we can't have the other work. So n will go from that to 0, which means the chain has left the table, which means now no longer friction is there, no longer work is there. So if this answer is minus mu times, what is the area, total area? I think the total area is very easy to find. Half into base into height. Correct? Half
Yes, sir.
base height. Sorry. And we're done. So the answer is minus mu mgl by 2, isn't it? Let's see if the answer is matching the formula which we got. So the answer is if I put x equals to L, what will get? L minus L by 2, which is L by 2 into L, which is L square by 2, which is same answer, right? You can see the answer is this one only.
Yes, sir.
Now, this is something easy to remember. Whenever you want to find the work done by friction, when the force is varying because of the decrease in normal, you just plot quickly the normal and x graph, find the area, and write work done equals to minus mu into area under the nx graph. So that is easy way for you to remember the answer. In case if you are forgetting the answer, if you know how difficult it is, stick to this method. So now comes the very interesting part, which is generally asked in a question also, that to find the velocity of change at the time of leaving the table completely. Now this is interesting. When the chain is about to, drop off the table. So we have seen the falling of chain, and we know that when it is about to fall, and this length is L, they will be asking you what is the velocity or the speed basically. So it's easy. We know that if the entire chain will fall, where is the center mass of the chain?
L/2.
Very good. So what is the work done by gravity? The total work done by gravity is how much? Because the entire mass has fallen. So you simply look at the gravity, the entire weight of the hanging part. So work done by gravity, how we write? The weight of the hanging part, weight of hanging part, mg is coming here, into the delta y seen. Correct? Am I correct?
Yes.
Delta y seen means how much center mass has gone down. So I'll put down, because it's like down means positive work, and if it is up, then what will be? Negative, because gravity acts downward. So how to write this is the weight is complete mg, and you can see clearly because the center mass has gone down, which is supporting the gravity. I mean, you can say the gravity is acting down and it is going down, so work is going to be positive or negative. Common sense. When the gravity center of gravity goes down, the work will be positive or negative.
Positive.
So it is positive. But in the same process, if you remember, what is the work done by gravity? Friction. It is exactly mu times, right? Mu times of this value, mgl/2. Correct? So generally mu is less than 1. So you can see that gravity is giving energy mgl/2, but how much friction is taking away? It is taking away mu times of that mgl/2, isn't it? So it looks like the mu is the factor by which energy is wasted. So I give you some money. Let's say if we give you 100, and if I say mu is 0.1, so 10% is wasted. So what I'll receive? Only 0.1 into what you give. I mean, how much I will receive? Sorry, what you give minus 0.1 times of what you give. So the whole idea is, what is the total energy achieved by the chain in the due process? Tell me. What is the total work done, guys? Hello, hello, hello. What is the total work done? So how much money you received in the due process? You receive mgl/2. How much you lost? So if you just add, you will get the answer. So this answer is mgl/2, 1 minus mu. Do you realize this?
Yes.
Yes.
And because this is the total amount received after loss and all. So how you're going to manifest this? So the work energy theorem states that the total work is equal to change in kinetic energy. So we have the answer mgl/2. And I know that the final kinetic energy is half mv², but initial was nothing. We just released from rest. And therefore, you can see a direct relation that mg so v² turns out to be 2, this 2 gets cancelled. The 2 gets cancelled. So what we are left with? GL. So V is. So such a interesting and easy answer, which can get for the total work done. You can do this easily for any chain problem. So chain problems are very famous problem, and because it comes under the variable force, so you can expect more questions on this in various textbook, booklet, examination, and so on. So make sure that you know something as basic as this, and you should be able to solve. Of course, when you study more, the same thing will become easy. When you practice more, then you will realize that okay, this is not so difficult. So at first go, it may appear difficult, but as you realize, as you start thinking in terms of energy, the process will be very easy for you. Okay. So now we are done with the chain problem. So we can go to the next concept, or to say a problem. So the same question can be asked in the reverse process. A chain is hanging off the table and someone is trying to pull it back. So this is a chain of length L. Mu is not given, or indirectly. This is the statement of the problem. A chain is hanging off the table with maximum possible length such that the chain remains at rest. Find the minimum work required by external agent to pull it back completely on the table. Okay. So now the job has changed. See, I haven't given you mu value, but it is logical. If something is at rest, can we imagine the chain at rest without friction? First of all, is it possible that chain will be like this if there is no friction between
No,
table
sir.
and the chain? So it's like logical. It is not possible that it is frictionless. It must be having some friction. So the idea is you as a student have to think about mu. I mean, mu will not be said or mentioned explicitly. It is indirectly possible that it should be there. Otherwise, we can't solve. So your first step is to solve for mu. What is the mu value? And it is clearly said that this is the maximum height I can hang. If I hang more than h, what will happen? The moment the hanging part is slightly more than h, it will start falling. So if it is at rest with maximum hanging part, which means the remaining part has achieved the limiting friction. Do you remember this concept? Limiting friction?
Yes, sir.
Okay. So because h is the hanging part, what is the part on the table? It is L minus h, right? So we can say the Fs max must be equal to Fs max on the table is equal to weight of which part? So do you realize? So the chain on the table will experience the maximum limiting friction and weight is trying to pull it down, and both are balancing. Any slightest movement on the right will let the chain to fall. So therefore, this we can write as mu. The mass is lambda L minus H mu m G. That's the limiting friction. Weight is lambda H G. Now, why I suggest to write in terms of lambda? You can see in most of the question, the lambda gets, so keep it simple. G gets cancelled. And so what you have left mu. So what is mu here? Now this is called the indirect way of getting the mu part. So mu was given to you, but not directly, but rather indirectly. The first part is done. Now begins the second part, how to start the assumption. Okay. So again, I will do it by the graphical method because we know that that's easy. And right now, where the center mass? The center mass is HY2, right? And what is the weight of the hanging part? Do you realize? The weight of the hanging part is lambda H.
Yes, sir.
Okay. Okay. So I'll just teach you how to do this. I mean, in fact, I hope you can do it on your own. Can you do it on your own? Do you have any realization how we can do? So for anything variable, what we do is we have to assume something in general at some instant. So right now that is given to you, but at any instant t, the chain on the table will definitely grow. But here you need to learn something more. How we make the variable, the assumption. So the agent is trying to pull towards the left. Let's say this is the agent. And because we are looking for the minimum work, so agent is pulling it slowly. Slowly means the force by the agent is equal to the net force experienced by the chain. So how to do it? Okay. So when you try to pull the chain, friction will try to oppose, and the hanging part will try to also pull. So if I now the question is how to assume the variables. Now which part is growing? The hanging part or the part on the table? Which part is increasing with time? The length of the
Part
chain.
on the table.
Part on the table. So always remember that the variable x we assign to the part which is growing with time. So that's why we call this as x. So this will become L minus x. Am I right? And
Yes,
therefore the weight will be lambda L minus x into G. And definitely the gravity work will be negative because it is trying to go up, right? You can see the gravity is acting down and it is trying to go up. So you can do the integration also, or you can do sometimes the integration is easy. I mean, you should do the integration. So work done by gravity is going to be positive or negative. How much?
Negative.
Negative. So minus m g dx. And you should be integrate from. Now that's the question. Where to where we have to integrate? So variable is x. So what was the length of x in the very beginning when you started seeing the question? What is x in the very beginning? So x in the beginning is, tell me what is x in the beginning? You can see the diagram, tell me. So total length is L and H is the hanging part. What is x on the table?
L.
Come on, L is the total length.
L minus H.
So
L
L
minus
minus.
H. So you can clearly see the x will grow from L minus H2 L.
L.
This is the limit. Now, if you realize the limit, you have mastered this question. This is very challenging question, not easy. Because student fail to realize the working part. Of course, later on you will be doing this with the concept of potential, but I would say that always learn the concept in the sequence. When it will come, that will become your additional method. Okay. So don't wait for that easy way and don't try to learn this slightly difficult way. You should know the intuition part very carefully. So work done by gravity is lambda L minus X into G into dx. And this is, if you can just mentally write this answer, like how to write, see, listen to me carefully, what I'm saying. I always say, and then write, I say M, G the force, displacement, which is the elementary displacement, and minus because of the direction. See, these are the steps which I do mentally. So I don't write the entire thing at once. I keep on doing this M, G, H, L, the weight into displacement. So always I write mentally the force into displacement, then I check the direction. If you have a similar visualization, what you're writing is already in your mind, it is not difficult. So do you get it? Tell me.
Yes, sir.
Okay. So now this you can integrate. I will keep lambda as lambda. So lambda G common and L minus X, we know Lx minus X square by 2. And this very cumbersome, L minus H. So which you will do. Okay, so this is solution, right? This is solution to the previous problem. And then what you do next is work done by friction. It's very simple. Minus mu. The normal will be weight on the table, which is lambda M. Lambda into X is M. See, listen to me, what I'm saying. Minus mu mg. Minus mu mg. Mu into N. N is mg. So mu mg. So mentally what I'm doing is I'm writing minus mu mg. So it's very simple. Into dx and I then integrate. So if you look at the process, whenever I'm solving, I am doing some mental calculation and I'm putting as it is. So work done by friction is for frictional force into displacement, and we know both are opposite. So again, the X will go from L minus X to L if I want to do the total work. So minus mu lambda G is common, I think. And then X dx is X square by 2. And you'll go from L minus H to L. So minus mu, let's do common. So we have L square minus. So minus mu G lambda by 2. And this is A square minus B square, which is A minus B into A plus B, right? So H into, this is the answer. Okay, so then you can write finally mu mg by 2L. Lambda I'm replacing now. At the end, we should replace. And that's it. So you can see things can be done. And if you want to write this part, so L, if you put upper limit, it is L square minus L square 2, which is L square by 2. And if you put the lower limit, it is L into L minus H. L minus H whole square by 2. That is the lower limit, correct? So minus mg by L. L square by 2 minus L minus H by 2 into L minus H. Okay, this looks lengthy, so I'm leaving as of this here. And then the question was not this. Question was, what is the minimum work done by the agent? Correct? So agent has to do work against both, right? So work done by agent is equal to what? And you're doing it slowly. So how many forces are working there? On the chain, agent is working, friction is working, and gravity is working. All are doing the, I mean, of course, negative work. So I will just add that all work is equals to changing kinetic energy. That is the work energy theorem. But because we are doing it slowly, so I'm not giving you any kinetic energy. So this will remain zero. We are doing it slow enough because we want the minimum work. And so you can see the working by force F, which we do not know, will be equals to the answer which you got minus W of friction in W of gravity. So once you substitute both, you can see both are negative itself. Minus will make it positive, which means whatever loss of energy is happening, you have to compensate by doing the work. Okay. This is not at all easy question. Don't think about it is easy. These are very challenging problems, and if you can realize these problems, probably you can actually get the hang of the variable mass, variable force problem. So these are like some of the challenging questions that you will come across at this stage. Of course, the difficulty level is enormous, which we can explore, but this is sufficient. And if you want to learn for the J advanced, this is sufficient, slightly good enough for advanced. Now you can practice with these ideas on even a tougher problem. Okay. So I hope you got the idea how to proceed with the chain problem. I have taken the two scenario, one when it is going down the table, when it is going up the table, both scenarios are discussed. So it means that completes the chain problem part. So we can move to something more interesting. I hope this is clear.
Yes, sir.
So So comes the next part, which is very, very crucial. See, in this chapter, we have done almost all variety of work. And this part is the most crucial part, that is called the work done by spring force. We all know that spring force is a variable force. So of course, we must learn about this force under this topic or this chapter, this subtopic of this chapter. So now the concept is called work done by spring force. So this is the most crucial part, and we can of course talk about a spring in slightly detail here as well. So we have done the spring in laws of motion on a very, you can say, basic elementary level, where we just understood the force definition, and that's it. Here I would like to just revise this concept once again, and I will draw some diagrams. So we have a spring. These springs are called the linear spring, and the linear spring having the property. You know what is the property of linear spring? Any guess? Just a minute. So there is a concept called linear spring. Linear means no, this is not the color. This is so a spring is said to be linear, in which the pitch length, if you see the helical shape of a spring in general, so the pitch length between any two consecutive part will be same. And when you deform, it will also become same. So if it is P and if you stretch it, so if you talk about the new pitch, it will still remain same, although new value, but same. And it means, and of course, these springs are massless. So we are having the assumption that uh, linear spring, constant pitch, massless. Okay. And now, when a spring is massless, it means something, and you're supposed to know what it means. Okay. So whenever a spring is massless, what we are supposed to remember? A massless spring refers to the fact that any force you apply at one end will transmit everywhere throughout the length of spring without diminishing, which means every pitch will deform independently of each other by same force, which means if I only take a small part of a spring, the deformation of that part is due to the applied force on the extreme end, because the force, although acting at one particular point of the spring, but its transmission will be same everywhere. Is this clear? So the note part we can add is for massless spring, force applied at one end will transmit throughout the length of spring without diminution. So this is not very difficult. I hope this is something you can understand. Without diminution. So as you go from, if you have a spring, so the force is not F at the rightmost end, rather, even if you check this point, you will see the same force F. Even if you check this point, you will see the force as F. So no matter where you cut, if you cut from here, it will also experience the force F here. Okay. And the other part will, even this part will also experience force F this side. So whenever you cut, the force you will experience is at that point, and it will have the similar behavior. What is the behavior means? If you're trying to stretch, it will be pulling the every portion of the spring. So the force is of pull nature in this case, as you can see. So the force is of pulling nature. Okay. And if a spring is under compression, if you cut, it will be compressing even at that point also. So, for example, if I have a spring which is compressed by something, and if you cut at any point P, okay, so what you will see that even at this point where you have cut, the force on the spring is again sorry, it is still compressing even at this point. So that is the nature of the spring force. It is simply get transmitted. Now, in a real life, when we have something massive, I mean, if we have a spring as thick as the spring of a moving train, the shock absorber of the train, if you look, it is a thick rod kind of turned into helix. And the weight of the train is so huge that it compresses that spring. But if you stand, you won't be able to even move by centimeter or that's too much, maybe millimeter. So your weight will matter nothing, because those are such a, you can say, powerful spring that only train weight of the train can kind of compress. So our weight will do nothing. So those are called massive spring. In massive, the transmission of force is not similar to what we study here. Okay. So the force is kind of, if you apply F at one end, it will diminish or it may increase, decrease depending on the situation, and it will go to the other end. So the whole idea is our syllabus is simple. We are not bothered about the variable, massive spring. Our spring is going to be massless throughout the discussion. Some property of spring that one should be aware of. Okay. So, of course, this is you will need also in chapter of simple harmonic motion, but one should be aware of certain things like this. So, what are the certain things? So the first thing is called effect of cutting of spring on spring constant. So this is something which is very common and you need to know for sure that if I have a spring of natural length L and the spring constant K. So what happens if I cut into two part, and if I say this one part is L1, another part is L2. So will it have the similar K spring constant or will it change? So that's the question. So clearly you can see that let's say it is having N pitch, and now when you cut, you will kind of distribute the pitches. So it will have, let's say, N1 pitch, and this is left with, let's say, N2 pitch or pitches, you can say. So we have these many pitches in the cut part. See, when you apply force, every pitch will elongate by same value. So if you give me less number of pitches, I will elongate by less value. Am I right? So under the application of same force, which one will elongate maximum? The biggest will elongate maximum, and the cut part will elongate less. Am I right? Hello.
Yes, sir.
So a shrinking in the elongation ability refers to that spring has become now more tougher, right? Because if you can't deform something by the same value, it means its spring constant has increased or decreased. The spring constant will increase as a result of cutting or decrease. Will it be tougher spring or milder spring? Tough or mild? What do you think?
So mild.
Oh, so if I give you a long stick, or maybe bamboo stick, and if I tell you, can you bend it? So probably you can bend if it is long. But as I make shorter, can you bend it easily?
No, sir.
So if I give you a pencil and if I say break it, can you break it easily? Yeah. But if I cut the pencil into 3 parts until you break the each part, do you think it will be easier or difficult now?
Certificate.
So if I give you a very small piece of pencil, maybe 1 inch, can you break it? It's very,
sir.
very difficult, right? The idea is as spring will shrink, its spring constant will grow in value. It becomes a tough spring. So the smaller spring will have more spring constant. That's the simple logic. So what we say and what you are supposed to remember as of now, that product of the spring constant and the length is always constant. So as this will decrease, this will increase. So the product must be maintained throughout. Okay, we have to maintain the product, and therefore a new spring we call K1, we call K2. But no matter what, the product of the two will be same as before. So this is the relation which you are supposed to remember, and therefore you can say the new spring constant of the first will be K L naught by L1, and similarly K2 will be K L naught by L. If you know the old and the new length, you can definitely find the old and the new K. This relation is very, 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 very important. Okay. So whenever you're cutting the spring, things will change, K will change. So you have to think that, okay, K will change. The second thing that you should be aware of in context of a spring is combination of a spring, how we combine a spring. So there is a concept. So there are 2 types of combination we all know. One is called the series combination. And I would like you to understand this by common sense. Tell me guys, if you attach a lot of spring in series, their elongation ability will improve or decrease? What do you think? They should be more flexible than before or less?
Sir, more.
Very good. So the stiffness of the combination will less or more?
Stiffness will be less.
Very good. So whenever something reduces, whenever some effect gets reduced, we use the reduced formula. And the reduced formula is very simple. We simply write 1 by K effective or K equivalent equals to, when something reduces, the inverse will grow. If some effect is decreasing, so the inverse effect will increase or decrease. We all know that if you combine 3 spring, then what will happen? If you combine 3 spring, then the effective K will decrease.
Yes.
If something is decreasing, so its inverse will
Increase.
Increase.
So see, this is how we remember things. Okay, this is like a memory aid. You are creating this idea to retain the concept in your brain that when we do something in series, if you make a bigger spring in length, definitely it will be more flexible because all can add up to some elongation, and therefore the K effective must decrease. And because K effective will decrease, so inverse of that effect must grow. So we say the inverse of K will grow. Grow means we add, correct? So you simply write 1 by K is inverse. You are increasing the inverse value, so the value will decrease as a whole. So this is a way to remember. Once you realize that which formula we should apply, If you understand that an increasing length of spring will definitely have the effect on this, you can always derive the formula correct way without getting confused. But if you go to chapter of current and electricity, if you remember from class 10th, if you add resistors in series, what do you think? The overall effect will grow or decrease? The resistance will grow in value or decrease in value? Tell me, what will happen?
Will grow in value.
And that's why if you remember in series, you should add the sum of the resistance, right?
Yes.
And in parallel, we used to add the inverse. We used to add the inverse. Because in parallel, it will decrease. So we used to add that the inverse of V will be inverse of R1, inverse of this, inverse of this. And this way of writing is called the reduce effect. So it is called the reduce K, reduce resistance. And if I use the similar thing, we call reduce mass. So the word reduced is used in this context. And as you go from chapter to chapter, it will appear, but you will never realize that what we are doing is a reduce effect. So we grow the reduce effect. I mean, kind of, we grow the inverse value. Whenever we see things are decreasing, we always try to increase, and to increase, we just make it inverse value. So these are something which will come across very often in physics. But this chapter is about spring, so we'll restrict this discussion until spring. This is the memory aid, but how to derive it? I mean, of course, this is not the proper derivation. Okay. So the rule is simple. Under the action of applied force, see, I have given you same force to everyone. So these are three guys, all are receiving the same force, but a different K means they have different elongation ability. So, and if I give you same force and if you have different ability, so what will happen? They will grow by different value. Do you realize this? What I'm saying? Hello, hello, hello. Do you
Yes,
realize
sir.
this? Okay. And therefore, because the first spring has elongated by x1, see x1, x2, x3, I am taking as elongation x1, x2, and x3 are elongation respectively. So you can clearly see based on the ability, they will have different elongation. If the K is same, in series combination, if you have multiple spring with same K, they will deform by similar value. A more K will less deformation and less K will have more deformation. And that will be the property of this nature. The product of the two is always constant. Anyway, so in series combination, the force transmission is F and it is equals to K1 X1, or see, listen, it is always or. You can write either K1 X1 if you know X1, you can write K2 X2 if you know X2, or you can write K3 X3 if you know X3. The thing is, we know nothing, so we write this relation, and from there we get the X1, X2, or X3. Okay. So having said this, when I say I would like to know the equivalent spring constant, I would like to know what is the K equivalent. Now, you can say that this K equivalent is the substitution of the three springs by one spring, which can deform by same value under this action of the same force as before. Let's say the ability of this spring to deform is X. Then to have this equivalence, what must be equal? What is the rule for equivalence? What is the rule for equivalence in any case? When these two springs are equivalent of each other, when the combination can be replaced by this K equivalent, what is the criteria? Tell me, what is the criteria? The criteria is the deformation in the actual case or in this hypothetical case must be same under the same force, right? So the criteria which will decide the equivalence is equivalent deformation ability under the same force. So we say that the X, as if this hypothetical spring will elongate, must be equals to how much? The net elongation you achieved previously. So this is the main condition you should understand. Condition for equivalence. This is the condition for equivalence. Do you realize this? Yes or no? Tell me. Do you realize this?
Yes, sir.
And now what we do is, because none of these are known to me, rather what is known to me is the F and K relation. So the next step is to find the K relation, you must substitute. So X can be replaced by F by K equivalent. Yes or no? Tell me. What is X1? F by? Do you realize this? And
Yes.
you can see the F gets cancelled. So what you are getting? 1 by K equivalent is summation of 1 by for any number. So I hope you remember or you understand as well how things are
Yes.
derived. Okay. And particularly you will come across for two springs in series combination, which you will come across. You can write 1 by K equivalent is, just write 2 times and then you can see the formula is K and K2. So if only 2 are there, you can do the product upon summation and you're done. Okay. And then you can do the similar thing. For n identical, I'll keep it small, it looks better actually. For n identical spring in series, which means if I write 1 by K equal to is 1 by K, 1 by K, and I have to repeat this how many times? N times. So can we write this as n by K? And so you can check that K equal to how much? Which simply means the effective K will reduce by K times. If we have identical effect, if you multiply the identical effect n times, the ability will grow exactly n times, and so the K will exactly decrease by n times. It will grow, so it will decrease by n times. I hope you realize this, what I'm saying.
Yes.
So if one spring, if you have 2 identical springs, so they will double the ability of elongation, right? So the K will exactly become half. If you triple the ability, K becomes 1/3. If you quadruple the ability, it will become 1/4. So if you make the elongation ability n times, the K will reduce by n times, isn't it? Hello. Because we know
Yes.
the product of K and the length is constant. If the ability grows by, see, the rule is KL is constant. So we can say K delta L plus L delta K equals to 0. Okay. So if we make delta L n times, you can clearly see that the delta K turns out to how much? Minus K. Am I right? K delta. So it is like the fractional decrease. Minus is saying that it will decrease. So as the length will grow by n times. Oh, I think I should have done. My bad, not contested. Because I'm differentiating, so it's like a under the calculus effect. So I cannot write the NL. It's a big difference. So we can write as K delta L is minus L delta K. Basically, you can say the loss in K is basically the incremental effect on the length will have decremental effect on the K. That's the whole idea actually. So that is always you can write as minus dk by k equals to dl by. I mean, then you can integrate and so on. I mean, of course, no need to do this. Things are like this. So one will grow, other will decrease because the product is constant. So you have to just remember this hyperbolic function. As the ability will multiply, the k will decrease. And if we know exactly the ability to elongate has become n times, I can without doubt say that the k will decrease by n times. Is this clear what I'm saying? Hello, 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 hello.
Yes, I got it.
Okay. So let's say, for example, if I tell you that we have three identical spleen of value k, k, k. So this is equivalent of one spleen of value, how much? What is the k equivalent here? All are identical, right? So the new k will be how much?
3 by K.
K
K
by
by
3.
3.
Do you guys realize this? What I'm saying?
Yes, sir.
Yes, sir.
Or you can use formula. See, always remember, behind every formula there is some logical step. So how we remember the formula? Of course, it's difficult to remember every formula. But if you remember the logical step, then it will help in recalling the formula in the examination. And the chance of making mistake will also reduce. Okay, just one. Okay. So we are done with the series combination. Let's think of parallel combination. And again, it's common sense. Come on. If you try to pull three springs simultaneously, what do you think? What will happen? The effort will grow or effort will decrease? So look at this common sense again. So let's say we have a block, and this block is attached to three different so you're trying to pull not one spring, but rather three spring. And definitely what will happen as you try to pull by same value, let's say you pull this block, or you can say the end of the spring by value X. So as a result, what will happen? To do this job, to let's say pull the block by X at equilibrium, each spring is pulling back by what value? K on X. This will pull by K2X, and this will pull by K3X. Do you realize this? That all are kind of opposing you whenever you are
Yes, sir.
elongating? Okay. So at equilibrium, and see, now we have a different way of approaching the problem. So this is called the parallel combination. So now at equilibrium, the applied force is balancing the sum of the three forces, right? And in this case, we have kept the elongation. So in parallel combination, all spring will suffer equal deformation, not necessarily elongation. It could be compression. But what we say is all spring will suffer equal deformation. Okay. So F equals to K plus K2 plus K3 into X. Now, again, the same question is, if whenever you want to replace a combination, and this is common sense, now the job of three spring is replaced by one spring. What do you think? The K equivalent will grow or shrink? Tell me. Under the application of same force, what I want is that the spring must suffer the similar deformation as before, which is X only. So the total deformation before was X, now should be X. So what do you think? The K effective is going to grow or shrink? You want to replace the three spring effective, three spring constant by only one spring in parallel combination. What do you think? Should it grow or should it shrink?
It should grow.
That's logical. You're trying to do the work of 3%, right? Alone. You must be powerful. Now, again, if you remember this diagram and this context, you can clearly say that F is simply, and because both are equivalent measurement, we can compare or equate. And so from 1 and 2, we can say K1 plus So the K equivalent comes out to be summation of Ki. You just need to add, which is very simple. No need to worry. And in this case, the K will grow. Okay. And if it is identical, it will become n times. If you add such n identical string in parallel, the ability will to pull, or you can see the string constant will grow by n times. Okay. Because parallel means they cannot have different deformation. Okay. They can have only equal deformation. One interesting part which will come across, which at first go doesn't look parallel, but it is parallel. So if we have one spring this side, and the object which you're trying to pull, maybe some mass, a block, or whatever, is in between, and on other side we have another spring in a same line. So of course the line is same. You're supposed to deform either this way or this way. So initially both the springs are at natural length. Now what you do is, let's say if you deform by either x right or left, if the ball is displaced towards right by x, you can clearly see something. The K2 spring will compress or elongate. K2 will compress or elongate. If I displace the ball towards the right, you can, by common sense, you can see the diagram and tell.
Compress.
The K2 will compress and K1 will elongate, right? So how the K2 will apply force on you? Right or left? When you compress, when you press something, it will press you back.
Yes, sir.
So the pressing force on the ball by K2 will be left or right?
Left.
Left.
Only tell if you realize, not because you are seeing on the this white or black board. What about the left spring? It is going to pull or push?
So pull.
Pull. In which direction?
So left.
Left. By what value? Yes. Do you realize that it looks, let's see, in a very first go, you may get confused that is it series? The answer is no. The two springs are not connected. Rather, we have two springs connected to an object, not to each other. And what you can see that the ability is getting added or subtracted. What do you think? The ability is increasing. Now it is difficult to move the object right to left, or it is easier. So imagine if I give you only K1 or only K2, will it be easier compared to when I give you both, or it is difficult when I give you both? Hello. The movement will be now more difficult or easier. So you can
Easy.
common sense. No? You are kind of, there are two spring, one is in front of you, other at the back of you, and you're trying to move. The back will try to pull you back. So it is making your walk difficult. It's difficult to move forward. And the front spring is pushing you back. So which is again making it even difficult, right? So the guy behind you pulling you and the guy in front of you pushing you. What do you think? The motion of the block will be difficult or easy when they both work together?
Definitely.
I mean, common sense. I don't know why it is not so common. I mean, this is common sense. Are you getting it? Yes or no?
Yes.
Yeah, Prashant, so tell me. Do you realize this is what I'm saying?
Yes, sir.
What do you realize? When I'll go right, what will happen? What is happening? Explain to me.
So then, like the question that you gave right now, right?
So explain this question. What is happening? If the object is moved towards right by value x, how the force will act on the, this object?
Towards the left.
So both force will be left only. So what is the net force acting on the object?
K2x plus K1.
Okay. And now if you want to replace by equivalent, so what I'm trying to explain that when two springs question come in which both springs on the two sides of the object, the idea is they behave as parallel. I'm not saying they are parallel, they behave as parallel. And therefore the K equivalent here is always the same as the parallel formula, it will add up. It is not series. Do you realize this? Yes or no?
Yes, sir.
So both springs are opposing, yes, isn't it? Both are opposing. Both are against the motion or supporting the motion.
Against the motion.
Both, na? Or individually only one. Both are against the motion or only one is against the motion. What do you think? What do you think?
So only one.
Only one. Okay, which one is supporting? When you're trying to go right, which one is supporting to helping you to go right?
So both are opposing.
Very good. So both are opposing. So the effect is parallel effect or series effect. So it's a parallel effect, right? Because in parallel, they do the same thing. They do the same. You can see the first diagram, all springs are pulling in the same direction, correct?
Yes.
And the third thing that you should be aware is, so this is the question which you generally come across in the chapter of simple harmonic motion, but you should learn this concept here itself. So let me give you some hypothetical explanation. We have some block and we have spring 1, 2, and 3. Let's put this is K1, K2, K3. I'm just trying to make it slightly better. And then we have K4, K5. Find K equivalent. What you can see that on the left we have too many, on the right we have too many. So first we have to make it left and right sorted first. So what is the net value on the left? How to understand what is the net value? So these two are in which combination? Series or
Series.
parallel? Series. So the left we can replace the top one by K1, K2. Do you remember for two spin this relation?
Yes, sir.
And the K3 is simply in parallel. So rest we are okay. And the right will be how much? K4, K5. And now these two are in which combination?
Parallel.
Parallel. Very good. So I can simply add them. So now I no need to write the two separately. I can write K3 plus K1, K2. And here we have only one already. K4, K5. And now we are left with only just two values, which are again in parallel or series. What is this combination? If you remember, these on the two sides of a block or object. So which combination? For
Parallel.
left, yeah, for left-right movement, it is parallel. And so we say the K equivalent is the sum of the two, right? Left plus line. Do you realize?
Yes.
Hello. Is this clear?
Yes.
All right. So you should realize that this is the K equivalent. This is the way of writing the K equivalent when things are like this. So in the chapter of simple, okay, see, not only in simple harmonic motion, even in this chapter, sometimes we do this trick to simplify the calculation. So if I have given too many spring, and if I try to solve each spring separately, it is slightly difficult. So what we do is we replace all spring by one equivalent, and then we have just one block, and from here we onwards we solve the problem. So that will reduce the entire effort tremendously. No need to solve things separately. So I will first reduce to this section, and then I'll think about my work energy theorem or something like this. Okay, so this is the spring part. I hope the spring part is clear to all of you guys. How to find the K equivalent is clear to all of you.
Yes.
There are some complex situations in which the springs are neither series nor parallel. So that I'll discuss explicitly in the chapter of simple harmonic motion. But just to let you understand that, okay, this kind of situation you will come across. So we may give you question like this. We have two springs. So this is theta. So you can see that, okay, if the mass will move this way, if the movement is vertically up and down, then these two springs will not neither behave as series or parallel. So these are not series or parallel. So here things will change. We have to understand a different derivation. It's called the, you have to derive from scratch. You have to displace and find the net force. And then you can replace that net force by K equivalent into. So if I displace by Y, my net force should be okay. So if you think this is L naught, this is L naught, this is K, this is K. So this must be if you stretch by Y, this must then it should exert a force of K effective into Y. This is, and the same force this particle must experience if when we stretch down. So later on, you will come to know that the net force it will experience is, I mean, of course, not now. It is 2K cos square theta. Yeah, it is like this one, 2K cos square theta. And here it is basically, sorry, into Y. And here it is K equivalent into y. So the equivalent k will become 2k cos square theta. So this is what we get as k equivalent. Okay. Understand what I'm saying? Hello, hello.
Yes, sir.
So, all right. Its derivation is not very difficult, but as of now, you can ignore. I mean, if I teach you right now, again, I need to teach you in the chapter, so I will avoid as of now. Just for your understanding, okay, this kind of question will also come. So, don't unknowingly apply the series parallel, because you need to have this realization that this is not applicable every time. The series parallel is only for the deformation of a spring when it is moving in the same direction, like either horizontal, vertical, or some fixed line of motion. Here, the spring's motion is very complex. You can see the elongation will let the spring to rotate, so things will not be easy. So, okay, let's go to the next part. The property of spring is to oppose the deformation, isn't it? Hello, hello, hello. Do you realize this? So let's say this is the spring of spring constant K with natural length L naught. Natural length means under the state of zero deformation, the length is L naught. When you're not deforming, the length is L naught. Okay. Now there are two possibilities. First, I can either compress. So if you compress the block, I mean, if you apply the force on the left such that the block gets, the spring gets compressed. If you compress, the length becomes L, which is less than L naught for sure. So under the compression, what is the act of the spring force? What the spring force will do? Will it push or pull? Will it push the block or pull the block?
Push.
So it will apply force on the right or left?
Towards right.
That's common sense. What you need to realize that every spring will try to go back to the original state or the undeformed state. X is called deformation. Do you realize X is deformation here?
Yes, sir.
A spring force not depends on the length, it depends on the deformation. So clearly the spring force throughout the compression event, the force has been acting on the right. Can we say? While you deforming, the force was right always? Oh, you can't say. Or you can say, tell me.
Yes, sir. Yes.
Yeah, yeah. Yeah, Prasans, are you getting it? What I'm saying?
Yes, sir.
Now I can do the similar thing. I can pull the block. And now, if you look at the original, this is L now, but this time it is more than L now. And this is your deformation. Under what state the spring is? Elongation or compression?
Elongation.
Why you guys are not seeing every note? And in the case of elongation, how the spring force will act? Will it try to go back to the original position? The force should act left or right?
Towards the left.
So on the block, it is acting left, correct? So what you realize, whether you're compressing or elongating, are you supporting the spring force, or it is against the spring force? Compression or elongation, both are against, or
Sir, against.
force and displacement are opposite or same?
Opposite.
In both cases, yes or no?
Yes, sir.
Okay. What do you think? The work should be positive or negative? So whenever we
So
try
negative.
to deform any spring, what we should expect? A positive work or negative work by the spring?
So negative.
Tell me, Prashant, what do you think?
So negative.
So whenever we have a negative work, what does it mean? The spring will give energy or take energy? So negative work done by spring on the block means what? Will it give energy or will it
So
take
it
away the
take
energy?
energy. Take energy from the block.
Okay, it will take energy from the block. Now comes the serious question. When you are taking the energy, are you going to waste or store?
Store.
So now, in this case, it's very interesting. The spring is having the ability to keep the energy taken. It is like a storing device. It never dissipates like friction. So friction also takes energy, but it will dissipate that energy. It will not keep it. It will just make it converted into some other form like heat or maybe light or maybe sound. So when you rub two things, you can hear these things. You can hear the sound. You can see the warmth, the heat produced, and sometimes you can also see some spark. So the dissipation of energy by frictional process will have three effects: heat generation, sound production, and light production. Among three, practically we have found that the majority, which means 99.9%, goes into heat generation, and less than 1%, maybe 0.001 or 0.01%, only creates the sound effect and the light effect. Therefore, in most of the question of frictional force work, we equate the loss only as a heat energy. I hope you will remember this fact. Is this okay?
Yes.
What you realize, whether you're compressing or elongating, in simple words, when you try to go from the natural state to deformed state, because these two together, what we can call, which state? And this is called or you can say un. So my question to you is, whenever a spring goes from undeformed to deformed state, what do you think? Will it do positive work or negative work?
Negative.
All right. So I hope you are understanding this fact. It is going to do the negative work, and therefore the work done by spring. Now it's a variable force or constant force. It is variable or constant. Which kind of force is spring force?
So variable.
So in that case, we have got the elementary work. So what, see, the rule is this. Okay, before I derive the formula, let me discuss things conceptually. Now, imagine the reverse process. You are here and you're going this way. So you're going from here to the natural state. What do you think? The spring will support or oppose? So when you go from deformed to natural, what to expect the work done by spring force? Or you don't think at all? Hello, 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 hello. Telling me guys something. If you
So
remain
spring
quiet, then
force
how?
will do positive.
So positive work means, will it give energy to the block or will it take energy away from the block?
Give energy.
And you know why it is able to give energy? Because while getting compressed or elongated, because that must have had been done by someone, they store the energy, and their spring is able to do the work, a positive work, because it is having some storage. So it is stored while getting deformed, and when it is getting or going back to the natural, the work becomes positive. So this is very interesting fact about spring force. It can do both kind of work, positive as well as negative work. Hello, yes or no?
Yes,
Mm.
sir.
Yes, sir.
So what we are supposed to remember, two very important sentence. Okay. You need to remember two things. Okay. Okay, so now there are two things. First, natural to deformed state. And remember, it could be due to elongation also, it could be due to compression as well. So deformed state is important, not compression or elongation. This is a common term. Deformed. You are deformed, yes, you're going from the natural to deformed, the work done by spring is going to be negative. But if you go from deformed to natural, in this case, the work will be, what do you think? The spring wants to go to natural, no? So when you do something,
Positive.
yeah, this is you're supporting, you want to go there, so the work becomes positive. So what really you come across in terms of numerical? Some interesting questions. Oh, what is the formula? What is the formula for work done? So I'll derive the formula itself here. So work done by spring force will be minus kxc f dx minus integration from 0 from no deformation, and we always write the deformation value as x. X is not length of a spring. Please remember, x represents only the amount of deformation that the spring has suffered. Okay. Some more key points about the spring force work. See, again, always try to listen to me what I say. I say I'm writing a formula minus f dx, and I integrate from no deformation to some deformation. And therefore, the answer is minus k x squared by 2. Here, the force is still kx, okay? And now you're trying to go to natural, so dx will be minus dx. Do you realize this, what I'm saying? Do you realize this fact, how I'm writing? Force, displacement. Now, what happens? This is somewhat confusing for many. When you go, see, I'm measuring the x from the natural, right? So if I move this way, the dx is increasing or decreasing. So if I call this is x, and if I call the new position as x plus dx, which one is bigger?
X.
X is bigger, no? So what is the displacement? The ds is how much? Big minus small, no? Correct?
Yes.
It is minus dx. Do you realize this? What I'm trying to do here? Whenever you try to go back to natural, your displacement should be expressed this way. Many should get confused. Why I'm writing like this? And then something more difficult to understand. You go from the deformed to natural. If you can hear this song, you have mastered the spring force. But even if you don't understand the song, always remember the lyrics, which is the answer is going to be positive. Not so easy, but not so difficult, because now we get the answer as minus k x squared by 2 from x to 0, which will give you the same answer, right? Hello, tell me. Do you realize what I'm doing?
Yes, sir.
Why I'm doing? In the first case, I go from actual x to a bigger value. So in the first case, the dx is positive, but when you go from x to a small value, and remember in calculus, we always write the initial as x and final as x plus dx. We never write minus, we write plus. Okay. And therefore the dx is negative, and therefore things in calculus, things are written in a very manner which is meaningful. When you write the f dx, you write the magnitude, right? If you remember, because we are taking the plus minus. No? So we know the direction. So we are writing value F into displacement, which is minus dx. So work done by spring is kx square by 2 plus minus. Now when to use plus, when to use minus, you have to think carefully in the question itself. So comes the some interesting problem in which this is natural. Let's say a spring is somewhere here, maybe attached to some block. Generally, this is the trend. And you are at a distance A, and now you go here at a distance B from here. Now, some book will tell you that, okay, let's say if you move B ahead like this. Okay. How to write the work done, sir? If this is initial, if this is final, my first question is, are we trying to recover or getting deformed more? In your journey, are you trying to go in the direction of force or against the force? Tell me. Are you moving in the direction of force? What is the spring force? Compressive elongation. What is the situation here? Is it compressive or elongation? Compression or elongation? Are you pushing the block or pulling the block?
So pushing.
Pulling.
Pulling. Because the natural is here. You're
Sure,
left of
sir.
natural. You're left of natural, right? So
Yes, sir.
spring is under compression or elongation.
Compression.
So you want to go back to natural. So will you push the block right or left? Like how the spring will apply force in the block? Towards right or towards left?
Towards right.
And I'm doing right now. If you look at the initial and final, don't you see I'm going from left to right? So what to expect? My work should be positive or negative?
Positive.
Now the formula is natural to deform or deform to natural, but there is no formula called deform to deform, natural to, of course, this is meaningless. So there's no formula for deform to deform because we haven't reached the natural exactly. We are in the process. So in such situation, you may get confused. So what we do is we think of what would be the work from here to here, or what would be the work from here to here. And by the relation we derive. So we say that W1 is W plus W2 because the subsequent work is equal to the full work. So W is W1 minus. This is how we derive. Because the formula is not for intermediate motion. Formula is only for the full motion. Unless you don't realize this, you can't solve question. So the problem is one should understand that the formula which we are using is only when you go from anywhere to natural or natural to anywhere. There is no formula for somewhere to somewhere. And that makes the spring work done sometimes very difficult for a student. They get confused. What is the relation part? These relation having certain validity condition. You can't apply as per your own will. You have to understand that how to apply correctly. So we can only write from the deformed to natural or natural to deformed. There is no other way of doing it. So do you realize this answer? How I have written? Yes or no?
Yes, sir.
W1 is from the deformed to natural. And you can see how much you move. For W1, the movement is X is how much? What is X here? For W1, what is X, guys? Tell me. What is the X value? What is the movement for W1? You can see the diagram. Tell me. To reach from the initial to the natural, how much you have to displace? Come on. Oh, you can't see anything.
A.
Okay, that's it. So if you realize this is A. So what? How to write W1? Is it positive or negative? First of all, just simple concept. Are you trying to go from natural to deform or deform to natural?
Deform to natural.
So work is positive or negative?
Positive.
Positive.
Plus half K A square. They're very simple. In your mind, you know it's positive. You write plus. You know the formula is half K X square. You write half K. You know X is A. If you think that way, it's easy. Minus. All right, all right. For W2, what do you think? Positive work or negative work? Come on, guys.
Positive.
Positive plus formula is half. Go ahead. K. Go ahead. How much you need to walk to reach there? What is X? Come on.
A minus B.
Very good. You're done. So your answer is half K A square minus A minus B whole square. And now if you want to simplify, it's A plus which is 2A minus B into 2. Okay, anyway, this is the most difficult part you will come across, or most challenging part of writing work, because you may know the formula, but if you do not know the exact way to apply, the chances are that you're going to make a big mistake. You have to practice this very carefully. All right. Shall we do the other problem or situation? Look at this. I'll give you some situation. Think logically and tell me the answer. I will use some symbol I for initial, N for natural, and F for final. Okay, I am giving you this is A, this is B, because I is given, F is given. Could you please tell me W is what is the work done by spring? If you can answer it, you're almost very close to the answer. So, what is the answer? What do you think? What should be the answer? See, you should never go from I to F directly. Whenever the natural comes, you have to always think from that perspective. We know the formula of only for here to here, and we know here to here. So what is the word by spring? What should we should write here? Tell me. Okay, W1. Okay, W1 is positive or negative?
Positive.
Positive.
Plus 1 by 2K.
A square.
And W2 is what? Positive or negative?
Negative.
Minus K. It's so simple, na? What's the problem? Come on, guys. Were you confused about the concept or apprehensive about the application? Like, should be apply or not? Do you realize how to write? Hello, hello, hello.
Yes, sir.
Yes, sir.
And the last thing, there are 3 cases only. So you are on the right of natural, even initially, and you go even finally, and I'll keep it simple. This is A, and I'll keep it simple as I said. This is B. So what is the work done by spin? Not this time, please answer. Don't say you don't know answer. Okay, do it.
So is it minus half K square minus half K B minus A whole square?
No,
So is it K by 2 A square plus B square?
no. You're not realizing that work is only meant for somewhere to natural or natural to somewhere. There is nothing like this. You want to go from I to F, so you want this work, right? Correct?
Yes.
Yes, sir.
But there is no way to find that work. Rather what we can find? We can find natural to initial and natural to final. So how to make the diagram? We know this work. And we can find this work. So what is my answer? My work done by spin should be how much?
W2 minus W1.
All right. So whether you try to find W1 or W2, tell me guys, the work is going to be positive or negative?
Negative.
Excellent. So for W2, what should I write?
Minus half K B square.
Minus half KB square. Very good. Minus. And what about W1?
Minus half K square.
Very good. Was it very difficult?
Yes, sir.
with experience, you will learn something. But that is with experience, so that's up to you. But is this the only kind of question I will come across? The answer is no. You have to learn something even more deeper about spring work. And you know what? The work is not about just linear deformation, compression, elongation. The work of spring only depends on amount of deformation, not the way you achieve that deformation. And that kind of question comes very often. So two things you need to realize. First, is it elongating? It compress? Am I moving away from natural? Am I moving towards the natural? Well, let's see what you can do on a different day. So one fine day you come across this situation. You're totally unaware. So a spring is attached to a, yeah, you got it right, to a ring. A ring which is able to slip on this pole. Do you see the ring? Hopefully, yes.
Yes.
And so this ring is able to move, slide, or do whatever, having mass m attached to a spring. And our spring in the very beginning is in natural length, L0. Natural. And it is perpendicular. So in short, this is the situation. And then you move, displace the ring. Oh, that's interesting. By X. Am I deforming the spring by X? No. So the new position of the spring is something like this. Nice. So my two questions which you need to answer. First, what do you think? Am I elongating or compressing?
Elongate.
Good. Right answer. My second question. Am I deforming from natural? So I'm going to from natural to deformed state or vice versa?
Natural to
Natural to deform.
Excellent. I'll call this as theta. Now look at this. The way I make the variable, you have to also learn to make variable in a similar fashion, especially in question like this. I have confused by giving x. This x has nothing to do with the x of spring force. Do you get it? Yes or no?
Yes.
Okay. So my question is, what is the elongation part? Delta L. L not is given. How to find delta L? Come on.
So using Trigo ratio.
Yeah, of course. So let's say the new length is L. What is the delta L then? L minus L naught. Am I right?
Yes.
But L and L naught are related to each other. L cos theta is L naught. What is L by the way? L naught sec theta. So what is delta L here? L naught sec theta minus 1. So delta L is L naught sec theta minus 1. Okay. Is this clear?
Yes, sir.
Yes.
Very good. So now you know the deformation. Generally, it's good to know in terms of theta, and of course, uh, you can find theta like because x is given. So tan theta is x by L naught. So cos theta is L naught upon under root of x square plus L naught square, and so you know the answer. I'm not saying you don't know, but don't write in this way in the beginning. Try to write it in the way I had written. Okay. So you got delta L. So what is the work done by spring? In this case, if I say this as initial, this is final, how one should write? So my question is very simple. Am I going from natural to deform or deform to natural?
Natural to deform.
So work is positive or negative? Go quickly. Work is
So negative.
Negative.
minus, how to write the answer? Minus half K. Yeah, go ahead. You're saying you're going right. Tell me.
Delta L.
Delta L whole square. Very simple. See, it doesn't matter how you deform. What is the shape of deformation? What really matters for the spring is the amount of deformation. If you realize this fact, any challenging question you can solve with ease. The condition is if you realize. Okay. So it will be difficult, maybe for some time, but if you put some more thought about it, you will master it. Okay. Let's see some more interesting problem. One more.
So can you
Yes.
please explain how you got delta L whole square? I mean, delta L square.
See, this is mathematics, and you can do it. Why think you can't solve it? Why it is so difficult? If it is so difficult, it means there's something problem with the mathematics. You know the initial location of spring, final location. You know theta. Delta L means what? Deformation is how much? Tell me. I have written everything. You can you read the lines written on the blackboard? Can you read
Yes.
from top to bottom?
L minus
And
L naught.
it doesn't make any sense to you.
Oh.
What is
So
L?
the
What is L
delta L
representing?
square I didn't understand.
What is L representing?
So the elongated length.
The length. So how much you got deformation? Delta L means deformation. How much you change the length of spring? Deformation.
L minus L naught.
And what is the relationship between L naught theta?
L is equal to L naught sec theta.
You realize this?
Yes. Sir.
Then how I got the answer? I simply substituted the value. I replace L by this value. What is the problem?
Okay, so got it.
Oh, good. So the work done is this much. My last question to you. And after this, you can solve any damn problem of the book. So it's a fixed hemisphere of radius r, and there is a small ball, and it is attached to a spring. And oh, excuse me, nice. It is in natural length. That's it. Now I start pulling this ball, maybe using some thread. I'm kind of pulling it. And after some time, I saw the ball to be here, which is making an angle theta. Well, this is initial, final, agent pulling the string slowly. Oh, wow. And the coefficient of friction is given mu. Oh my God. Yes. Let's go one by one. What are the forces you can expect here? Acting on the block, on the mass, normal. Kinetic friction because it's slipping. And one more force. Is spring force. Do you realize this? And one force, of course, tension. So how many forces are acting? I think I should draw separately. ABD at theta. You draw the, and because this is theta, so you know this is. If it is like tangent, this is tangent. So this is theta. So this is tangent. So this is of course 91 theta. But anyway, my object is here. If I try to draw the ABD, and because I'm trying to pull up, what do you think the force acting on this block should be? In which direction? So gravity will act like this. I hope you're okay. Friction will act in which direction? Down the plane or up the plane? Hello, 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 hello.
Down the plane.
Down the plane. Excellent. And normal? Like this. So the forces are normal reaction, mu into n, when the friction, m into g, gravity, and of course, the force, one more force which we didn't realize was the spring force. And of course, the agent is doing something. So that force should be taken into consideration. The tension, which is actually equal to the applied force F. So these are the forces. Oh my God. Yeah, these are the forces. Nevertheless. So for equilibrium is what? For slowly means what? Equilibrium is always maintained. These are like very challenging problem, very challenging Olympiad problem for you. So for equilibrium, how to write? Net force equals to 0 along the tangent. Yeah. So mg will have two components. Mg is cos theta down the plane, and mg is sin theta like this. Yeah, but anyway. So let me write down. Along the tangent, I can say F upward equals to mg cos theta downward, because the slope is 9 theta. Friction force is yeah, mu mg sine theta. Spring force is k. I need to find the deformation k delta L. This is the force. So if I move slightly ahead, if you go slightly ahead, slightly like this, I'll call ds, the elementary displacement. If I call this is d theta, so we can add ds equals to r d theta, which is sometimes convenient. So the elementary work by the force, because we have so many force, is f ds. Oh, that's simple. Which means mg cos theta ds mu mg sine theta ds and k delta L ds. Oh, delta means dl. Yeah, I mean, no, k delta L ds. Correct. So much effort, right? But we have done this before. I mean, I'm not trying to use that relation which I have derived, but I'm doing it again. The ds cos theta we called dy, which means vertical displacement. Mu mg ds and that's called, my bad, ds is like this. Oh yeah. So this time this is theta. So ds cos theta is dy and ds center is dx, correct? So ds and theta is dx. Well, it's fine. And delta L. What is the delta L in this case? When you go from initial to this position, you go from here to here. At in general theta, what is the elongation you think? How much spring has grown elongated? Come on, come on. Yes, you can do it.
R
Yeah.
theta.
Very good. And then ds I can write as r d theta. You know why? Because I know this is the variable, so I should express the answer in a similar type. Well, I could have written the same for all other, but this is easy for me. And then I write the net work done by F, which is integration of BWF. And the rest I know. I mean, we have done this before. So if you reach here, this is your total X, this is your total Y. So the delta X is X, which is R1 minus cos theta. And delta Y is Y, which is R sin theta. In general, if you want to solve a general answer, so the answer will be mgy. I mean, of course, dy you integrate from 0 to y, mu mgx and plus k r square theta square by 2 from 0 to theta, which is, I did all the integration without writing. I hope you can understand. And then this very challenging problem is now solved. So the answer is mg r sin theta. In general, we are solving for theta angle actually. Like what is the work done if you go from I to F? That's why we are solving. So mg r sin theta plus mu mg r1 minus cos theta plus k r square. Like, this is the work. So maybe you want to go from bottom to the top. So theta is 90 degrees. You will get some real nice answer. So if you go to the top of the sphere, hemisphere, what will you get the answer? Sin 90 is 1, so mgr, which is logical because if you go r above, the work done by gravity is going to be minus mgr. So Here it is coming overcome by F. Mu mgr only. That's cos 90 is 1, cos 90 is 0, so 1 is 0 is 1. And then this is kr square. This is pi, we should write in radian, pi by 2. So this is the mg we can take common, mgr we can take common. 1 plus mu plus k I square. So interesting. You can see these kind of questions you can solve now with ease. I mean, oh, if you realize. So with this, I'll stop my discussion. Your homework is the entire SC Verma. Try to solve each and every question. And next class will start the energy relation. So this today's lecture is very, very important. You have to revise it thoroughly till you realize. Revise till you realize. Don't skip today's lecture. Don't try to go to study something else. No. If you haven't understood this chapter, you should study right now carefully. Spend time, do the calculation, make some relation for yourself, and once you realize, you always know it's easy. So I hope so. Bye and take care. You know the homework. You can solve the, if you want to solve SC1, you can solve entire Solomon, you can solve entire resonance booklet. Now it's easy for you. Okay. So bye and take care. See you in the next lecture.
Bye, sir. Thank you, sir.